In this video, I will be talking about kinetic and potential energy. I will also talk a bit about work since work is a transfer of energy. Please refer to the timestamps below if you would like to see a specific problem. First, let's define what kinetic energy is. Anything that moves has kinetic energy. If a ball, an object, or a particle have some speed and some mass, then they will have kinetic energy. The equation for kinetic energy is equal to 1/2 times mass times speed squared. The mass is in kilograms, the speed is in meters per second, and the kinetic energy in joules, which is the unit that measures energy. But what is actually energy? Energy is the capacity or ability of something to do work. If work is done on an object by applying a net force and the object speeds up, then we can say that the object gained kinetic energy. The work kinetic energy theorem states that when work is done on a system and the only change is in its speed, the net work done on the system is equal to the change in the kinetic energy. In an equation, that just means that work equals the change in kinetic energy or the final kinetic energy of an object minus the initial kinetic energy. Now, we have seen work in the previous two videos, but what exactly is work? Work is the force times the displacement times cosine of theta, where theta is the angle between the force and the displacement. Work done on an object is proportional to the force we apply on the object. If the force is not constant, then we can calculate work done on the object by solving the integral of force times dx. I am adding at the top the two videos that explain these two equations. Now, if we stop here for a second, you can find the kinetic energy if you know the work done, and find the work done if you know the kinetic energy by making these two equations equal to each other. We will see some examples later. I suggest that you write these equations now since they're the ones we will be using for the problem. Now, we can move on to potential energy. This is a little bit more complex to understand. Basically, it is the energy stored in an object due to its position relative to some zero position. For example, gravitational potential energy is the energy stored in an object relative to its height from ground. Let's imagine a system consisting of the backpack and the earth. We do some work on the backpack by lifting it up some height from the ground. Since there was some work done on the backpack, we know there is a transfer of energy as well. After lifting and holding the backpack, we can release it and let it fall back down to the ground. Then the backpack will have some kinetic energy while the backpack was at the highest point. However, it had the potential to possess kinetic energy. Therefore, the energy storage mechanism before the backpack releases is called potential energy. More specifically, we can call it gravitational potential energy. The equation we use to calculate gravitational potential energy is mass times gravity times height. I will call y in these problems, but you might see it as h for height as well. And again, we can consider the work done as a change in potential energy. In this case, we will see as the initial and the final height of the object. Now that we have all of our equations, let's start our first problem. Problem number 1. A 5 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force of 15 newtons. Find the block's speed after it has moved 5.0 meters. We are asked to find the final velocity. The equation we know that has velocity is kinetic energy. However, the other two variables were given apart from mass are force and displacement, and we can find the work done by multiplying the constant force times the displacement. We can always connect work to energy since we know work is just the change in energy. So, since work equals final kinetic energy minus initial kinetic energy, but the initial velocity is 0 since the object started from rest, so work equals just the final kinetic energy, then work equals also force times displacement times cosine of theta, but the force was applied horizontally as well as the displacement. This tells us that theta angle is 0 as they were both going on the same direction, and cosine of 0 is just 1. So work equals force, which is 15 newtons, times displacement, which is 5 meters. Work will be 75 joules. Now we can plug this into our previous equation and rearrange it to solve for velocity. So the final velocity equals to 5.47 meters per second. Problem number 2. A dumbbell slips from an athlete's hand and drops on his toe. Choosing floor level as the y equals 0 point of your coordinate system, estimate the change in gravitational potential energy of the dumbbell-Earth system as the dumbbell falls. We are told here the initial height is at 1.20 meters, which is where the athlete was holding the dumbbell before he fell down. Then the final height is at 0.02 meters. We can easily just solve for the change in potential energy by solving our equation for gravitational potential energy. So mass times gravity times final height minus mass times gravity times initial height. Let's plug in our values. And the change in gravitational potential energy is then minus 17.31 joules. Now remember, the higher you are from the ground, the higher the potential energy you have. So if you're moving away from Earth's gravity, you will store more potential energy. And if you fall down to Earth, you will lose that potential energy. It makes sense that since the dumbbell fell down, the change in potential energy is negative. You should keep that in mind when answering these types of questions. Let's move on to problem number 3. A 0.525 kilogram particle has a speed of 2.00 meters per second at point A and kinetic energy of 8.5 joules at point B. What is A, its kinetic energy at A, B, its speed at B, and C, the net work done on the particle by external forces as it moves from point A to point B? So I will draw how the particle moved and the points so it is visually easier to understand. The particle moved from point A, where the velocity was 2 meters per second, to point B, where the kinetic energy was 8.5 joules. We must find kinetic energy at point A and velocity at point B. Let's start by finding the kinetic energy at point A, which is very simple since we know the mass and the velocity. We just need to solve for the formula we have. Kinetic energy equals 2/2 times mass times velocity squared. So let's plug in our values here. And the kinetic energy at point A is equal to 1.05 joules. Now let's solve for velocity at point B. We know it is the same equation, we just need to rearrange it and solve for velocity. Velocity equals to 5.69 meters per second. Now, the net work is just the difference in kinetic energy. So the final kinetic energy, which is kinetic energy at B minus the initial kinetic energy at point A, that equals 7.45 joules. Now, let's move on to problem number 4. A 5 kilogram object has a velocity of 6.00 I minus 2.00 j meters per second. What is its kinetic energy at this moment? What is the net work done on the object if its velocity changes to 8.00 I plus 4.00 j meters per second? I love this problem because it involves a little about everything. However, you must know how to calculate the dot product in this case. So we need to find the kinetic energy when the object has velocity of 6.00 I minus 2.00 j. We know kinetic energy is just half times mass times velocity squared, and the velocity squared is equal to v dot b. So let's first solve for the dot product. It is very easy to solve. We just need to multiply I with I, which in this case is 6 times 6, and then add that to multiplication of j times j, which in this case is minus 2 times minus 2, which is just plus 4. So 36 plus 4 equals 40. Now we can just plug that into our kinetic energy equation as velocity squared. So kinetic energy equals half times 5 kilograms times 40, and that is just 100 joules. For the second question, we must find the work done if the object increases the velocity. So we can calculate the kinetic energy at that velocity and then calculate the change in kinetic energy. So let's first get the dot product for velocity. Then we can plug that in again and get the kinetic energy. To get the work, we must get the difference, so the final kinetic energy minus the initial work will equal 100 joules. Now let's move on to problem number 5 and our final problem. A 0.250 kilogram stone is held up 1.5 meters above the top edge of a water well and then dropped into it. The well has a depth of 3.8 meters. What is the gravitational potential energy of the stone-earth system before the stone is released and when it reaches the bottom of the well? What is the change in gravitational potential energy? So this problem is again regarding gravitational potential energy. I will draw a diagram here showing what is happening and the heights of the stone so we can visually see the movement. So y equals to 0 at floor, then 1.5 meters above the ground and 3.8 meters is below it. We must then indicate 3.8 meters as negative as it is below our 0 position. So we can now just calculate m times gravity times height. Now that we have solved for A and B to get the change in gravitational potential energy, we know it is final potential energy minus the initial, and the change will equal to minus 12.98 joules. Okay, so that is it for this video. I hope the explanations and problems were useful. Please let me know in the comment section if you have any questions. Thank you so much for watching.